Hello and welcome to Gaffy's Grinds. This is a YouTube channel dedicated to helping you guys learn about leaving cert chemistry. So we're going to take some leaving cert concepts, topics, we're going to break them down into small, simple, manageable pieces. We're going to explain them so that you'll understand them in, as simply as possible. And then the really important part that we do on this channel that I think is different from other channels that makes this channel unique is that we do a lot of practice, and practice is what helps you convert stuff that you're learning into your long-term memory and make sure it's there when you need it. So that's what makes us unique from other channels, I believe. So with that in mind, just a couple of reminders. It's really important that if you're going to watch these videos, you give them your full attention. So please eliminate any distractions by putting your phone on do not disturb, or even better, if you can stick it in another room for a while you watch the video. It's the number one distraction. It happens to us all. And if we can just eliminate the possibility of a message going off or a phone going off, it just means you can give this your full attention. And then, as usual, like I said, our unique selling point on this channel is the amount of practice that we do. So it's really important that you do the practice exercises during the video. If not, you are really wasting your time. I can't make you do them, but if you're going to put the effort in to watch the video, you may as well do the practice and make sure you're actually learning properly. So before we jump into today's topic, we're going to be looking at something called the atomic radius. But before we do that, we're just going to quickly do some practice. Some retrieval practice where we look to see if we can retrieve information we've learned before. So this should be information that we've learned before about the periodic table. So if you haven't seen my videos on periodic table, you will find them in another playlist on this channel. So what I'm going to get you to do is I'm going to get you to do these questions. I'd like you to pause the video while you do them. Now, before you pause the video, just make sure you've got a pen and a pencil and a paper somewhere to write these questions down. So in your own time now, I want you to pause the video and try and answer the questions in full sentences, please. Full sentences just makes your answers more concrete, and it gives you actually a better chance of remembering them because sentences link ideas together. So full sentence answers, please. Pause the video and do these now. Okay, so we're just going to go through them now. That's what we normally do. You do practice, then we go through them. Sometimes if I think they're easy questions, I'll just throw up the answers and you can correct them yourselves. So with a correcting pen, a different color than what you've written in, we're going to correct these now. So why is the periodic table referred to as the periodic table of elements? I'm actually just going to put the answers up here, guys. I'm going to have to stop to help you. I'm going to have to stop to draw some of them. So here is question 1. Have a read of it yourself. Check your answer now and see if it says something. It should be very similar along the same lines or meaning the same thing. If not, then by all means pause the video and correct it. Now, why is it called the periodic table of elements? Well, it's periodic table of elements because it contains all the known elements and it has repeating patterns. So it's a periodic table. So periodic means repeating, and table is obviously it's a table, and it's the periodic table of elements because it's got all the elements that we know of. Right. Number 2, what does the group and the period that an element is in tell you about its electrons? So the group and the period. So the group number tells us the number of electrons in the outer shell. So if it's in group 2, it'll have 2 electrons in its outer shell. If it's in group 4, it will always have 4 electrons in its outer shell. Group 7, it has 7 electrons in its outer shell. So we learned about that little shortcut for working out the number of electrons in the outer shell. And what about the period? Well, the period it's in tells you what energy level the outer shell electrons are in. So if it's in n equal to 3 energy level, then the valence electrons are in n equal to 3 energy level, and they've obviously got 3 energy levels. Then it's got electrons in n equal to 1, electrons in n equal to 2, and electrons in n equal to 3. If it's helium, for example, helium is in n equal to 1, then it's got electrons in n equal to 1. It does not have electrons in n equal to 2. It does not have electrons in n equal to 3. Okay, so that's what that tells us. Number 3 says, draw a simple Bohr atom of lithium. So a simple Bohr atom of lithium. So you're probably going to need a periodic table for this. So pause the video and go and get yourself a periodic table. Okay, so this is what you should have drawn. We should have a lithium nucleus, so Li, and Li has 3 protons and 4 neutrons, because the mass number is the atomic number is 3, which means it's got 3 protons, and the mass number is 7, which means it's got 7 protons plus neutrons. And to work out the number of neutrons, you do the mass number, take away the atomic number. Again, I'm rushing through this, but I'm expecting that you guys already understand this. So if not, you need to go back and watch where we drew the structure of atoms. So that's the nucleus, 3 protons and 4 neutrons in the nucleus. Now, I'm just going to make that a little bit neater. Okay, so that's the nucleus. We then draw the shells, or the energy levels where the electrons is. So this is the first shell. Now I'm just going to fix this circle. I don't like where that's gone on me. So the first shell. Okay. All right, anyway, you get that. I actually need to fix that. Not happy with that. All right, that'll do. We'll have to leave it like that. So the first shell has 1, 2 electrons, and we have 3 electrons altogether. So there is the third one. So we've got 2 in the first shell and 1 in the second shell. So these are energy levels, okay? Number 4, what charge will lithium take when it becomes an ion? Well, lithium's in group 1. That means it will lose this 1 electron like this. This electron will get lost. Another atom will take that. So now it's got 3 protons. So it will have 3 protons, which means 3 plus charges, plus, plus, and plus, because each proton is positively charged. And now it's only got 2 electrons because it's lost 1. So we've got minus and minus. So overall, we've got 3 plus charges and 2 minus charges. So these two are obviously equal and they cancel out. So we have an extra plus charge. So we're going to have Li plus, lithium plus. So we'll take a plus 1 charge. That's answer to question 4. Question 5, 2 different elements chemically react and combine together into a single product. What word can be used to describe the product? Product is a compound. So compound is 2 or more elements chemically combined. Well done if you got that right. Number 6, chlorine is a simple molecular substance. State 2 of its properties. So a simple molecular substance. So we previously learned about the properties of ionic substances and covalent substances. So a simple molecular substance like chlorine is a covalent substance. Okay, so it's covalent. Now, if you didn't know the answer to that and you didn't know it was covalent and now you do, maybe you can remember now properties of covalent substances. Then you can pause the video and write that down. Okay, so this is what you should have. Covalent substances, so simple molecular substances, will always have low melting and boiling points, and they do not conduct electricity. So simple molecular substances, because there are no charges, we do not have ions, it does not conduct electricity, and they will have low melting and boiling points because the forces of attraction that hold the particles together are weak. Okay, again, all of this is previously learned knowledge, so I'm hoping that you guys already have a good background here if you've watched the previous videos. Rubidium reacts with water. Would you expect potassium to react with water? Explain your answer. Now, if you had no idea about this, you're going to need to go and look in the periodic table and have a look for rubidium and potassium. So go do that now if you weren't already able to figure this out. Okay, so hopefully you realized, and if you weren't able to find them, you should now look for them in group 1. So have a look at group 1. Okay, so in group 1, you will find potassium and you will find rubidium. So I suppose here, when we did periodic table, we would have learned that elements are in the same group, or they're put into the same group if they have similar chemical properties. So if rubidium and potassium are in the same group, that will mean they have similar chemical properties. So now that you know that, if you haven't already written an answer, maybe you can write an answer now. So pause the video. Okay, so rubidium reacts with water. Would you expect potassium to react with water? The answer is yes, you would, because they're in the same group. Elements in the same group have similar chemical properties. So that's question 7. Yes is the answer, but it asks you to explain your answer. Yes, I expect this because elements in the same group have similar chemical properties. Number 8, in terms of energy levels, what happens when you move down a group in the periodic table? What happens when you move down a group? So in terms of energy levels, well, if we just very quickly take, for example, group 1. So group 1 has lithium, sodium, and potassium. Lithium is in what we call the N equal to 2 energy level. Sodium is in the next line down, the next period, N equal to 3 period. And potassium is in the N equals to 4 period. Now, there is no element in group 1 that's in N equal to 1. So N equal to 2 is lithium, N equal to 3 is potassium, and N equal to 4 is, N equal to 3 is sodium, and N equal to 4 is potassium. So in terms of energy levels, what happens when you move down a group of the periodic table? Well, if you weren't already able to answer it, maybe you can now. Okay, so the answer here is that when you move down a group in the periodic table, the number of energy levels an atom has increases. So if we compare potassium in N equal to 4 to lithium in N equal to 2, those periods, potassium is in the N equal to 4 period because it's got 4 energy levels. Sodium has 3 energy levels, N equal to 3, and lithium has electrons in 2 energy levels. So as you move down the table, the number of energy levels increases. Number 9, in terms of protons, what happens as you move from left to right across a period in the periodic table? So say, for example, we took the N equal to 2 period. N equal to 2 period begins with lithium. So I'm going to begin it here. Now, if we draw the next one beside lithium is beryllium, Be. And then there's a big gap in the periodic table. If you take a look at your periodic table, there'll be a big gap. There won't be any other elements in the N equal to 2 energy level until you get over to here. The next element here is boron. And the next one is carbon. Okay, so what's happening in terms of the number of protons as we move across the periodic table? Well, of course, we have learned that it's the atomic number that tells us the number of protons. Now, the atomic number of lithium is 3. It's shown on the periodic table as the smaller number attached to each element. So lithium is 3. Beryllium beside it is 4. Boron beside it is 5. And carbon is 6. So the pattern we see here is as we move from left to right, the atomic number increases by 1 each time you move from left to right. Now, if the atomic number goes up by 1, that means the number of protons goes up by 1 because the atomic number tells us the number of protons. So the answer here is when you move from left to right across a period of the periodic table, the number of protons increases. So that would be the correct answer here. All right, so that is just some recap questions. Now, before we begin, like I said, we're going to be talking about something called the atomic radius. And before we do that, I would like us to just have a quick go at these questions about generally a circle and radius and stuff like that. And you just need to make sure you guys have a basic understanding of a circle before we begin. Should be very straightforward. It's very basic maths. You would have done this a long time ago, but I just want you to do this for me now. So pause the video, please, and try questions 1 to 4 for now. Just do 1 to 4. Pause the video. Okay, so you should only be watching if you have done questions 1 to 4. So the first thing it asked you to do was draw a circle. So I'm going to draw a circle here. So you had to draw a circle like that. That's all you had to do. Then number 2, add and label the midpoint. So this was checking to see, do you understand where the midpoint is? It's here in the middle of the circle. So we find a midpoint in the middle of the circle. And I'm going to label it here in red. This is the midpoint. It then asks you to draw and label a radius. So I'm going to take my ruler, the snazzy cool ruler, and I am going to draw a radius. I'm going to pick a different color. I'm going to do it in green, and I'm going to label it. So for a radius, what you should have is you should have a line which connects the midpoint to the edge of the circle. Oh, that's too thick. I'm going to make that a little bit narrower. A line that connects the midpoint to the edge of the circle. Now I've done that from the midpoint to the very right of the circle. But, and this is important, you could put that anywhere from there to there is also a radius. From there to there, like this, is also a radius. From there to there would also be the radius. All of those lines would be the same length. So it doesn't matter where you do it. The midpoint is always a constant, it's always a constant distance from the edge of the circle in any direction. That's the beauty of a circle. The radius out to the edge is always the same distance. So I'm just going to delete those lines and just go back to 1. So draw and label the radius. So you should have had that done. And then this is radius. Now, the next question says measure the radius with a ruler. So what I'm going to do is I am going to do that now with my ruler. And here is my 0. Now, each of those solid lines here, if we look at the ruler, I'm just going to show you here, if this is 0 there, then that is 1 centimeter, the full line here. So it's a bit bigger than the rest. Would be 1 centimeter. That would be a 2nd centimeter. That would be a 3rd centimeter, and so on. And that means that each of the little lines is a centimeter divided up by 1, 2, 3, 5 spaces. So each of the little lines is 0.2 of a centimeter. So I just wanted to point that out to you. You guys will have a ruler that's got numbers on it. Unfortunately, this one doesn't, which is a pity. But anyway, we're going to put that on the midpoint and out to the edge. That is going to be 1.6 centimeters. So my radius or equals 1.6 centimeters. So you should do the same. Now this seems silly. We're talking about chemistry. Why are we doing maths? Well, I just want to make sure that you guys know how to, the concept of drawing a circle, what the radius means and how you would measure it. So once you have a circle drawn and you know where the midpoint is and you know where the edge is, it's easy to find the radius. You just draw the line and you measure the length of it. Now, that's going to be important to help us understand what we mean by atomic radius. But before we do that, I want you to first try and recall from when we did atomic structure, again in a different set of videos here, but we're always practicing retrieving. What is the Heisenberg uncertainty principle? What is the Heisenberg uncertainty principle? So pause the video now and see, can you write down the definition for the Heisenberg uncertainty principle? Okay, so the Heisenberg uncertainty principle is basically, it states that it is not possible to know or to be certain about the position and velocity of an electron simultaneously. Now, simultaneously just means at the same time. So in other words, you can't know both the position and the speed that or the velocity that the electron is traveling. It's not possible. You can't know them both at the same time. Now, there is a very good reason for this, and I explained it in the video when I talked about Heisenberg's uncertainty principle, so I won't go into it here. But it basically leaves us very uncertain about where the electrons are at any particular time. It's not always possible to know exactly. It's not possible to know exactly where the electrons are and where they can go in an atom. Now that's going to create us a problem when we want to actually learn about what the atomic radius is. Okay, so I'm going back over here and we're going to start talking about atomic radius. So to measure the radius of the circle that we just did, you measured from the midpoint to the edge of the circle. The distance will be consistent from the midpoint to any point you choose on the edge of the circle. You can pick any of the points on the edge of the circle, measure the distance from the midpoint to there, and the radius will always be consistent. It will always be the same. Now, to measure the radius of an atom, if we wanted to take an element, say hydrogen, and we wanted to measure the radius of it, we generally tend to represent atoms as spheres, or as spheres or circles on page. So why can we just go and measure the radius of the circle? Well, of course, if you wanted to do this, you would need to measure from the midpoint, which in an atom would be the nucleus. And what we would need to do is we would need to measure from the nucleus, which would be the midpoint, to the electrons in the outermost energy level. So wherever the electrons are in the outermost energy level. So imagine there we have an energy level. Now, of course, that's not great because the nucleus there is not in the middle. Right, so what I'm actually going to do is I'm going to rub out the nucleus and put it in the middle because I don't like, there, now that's better, nucleus. And wherever the outermost electron is, say that's it there. Actually, I'll do it in a different color so we don't mix them up. Say the green one is the outermost electron. We would want to know what is the distance from the nucleus out to that electron. Now, a problem though is a consequence of the Heisenberg uncertainty principle is that it's impossible to determine the exact outer edge of any energy level, because according to Heisenberg and what you now know about orbitals, etc., we're not exactly ever sure exactly what distance the electron is from the nucleus. We know that it spends quite a lot of its time in that space, but it could also be here, and it could also be here, and it could also be here, and it could also be here. Now, most of the time, it's somewhere, it's orbiting somewhere around here. But sometimes it gains extra energy and it comes out to these locations. Sometimes it loses energy and it drops into these locations. So orbitals are really just an average position. Taken where does the electron spend most of its time, and it's basically given us a picture of where the electrons are most of the time. So because it's actually not possible to find out exactly where the electron is, you can't just draw a line and measure it. So to overcome this problem, scientists have come up with an ingenious way, a brilliant way to infer this information, to basically figure out if you can't actually measure from the nucleus to the outermost electron, how do you find the atomic radius? Well, basically, how this works is, I'm just going to get rid of that now for a second. Scientists use X-rays, and what they do is they take molecules which are made of two atoms of the same element, like this. So we've got one circle, and what I'm going to do to make sure they're the same size circle, I'm going to copy this like this, and we take two atoms of the same element, so that means they're both the exact same, they're the same size. We've got a molecule that's made of these two exact same atoms, two identical atoms. And scientists use X-rays to measure the distance between the midpoints of these circles. Okay, so they can use X-rays and they can find out, X-rays can basically be used to figure out what is the gap between these two nuclei. So basically what we're talking about here is we're going to take the gap between this nucleus and this nucleus like that, and we're going to measure the distance between them. So how far is that distance? Now, if we take this distance and divide it by 2, then that will give us the atomic radius. This is called the atomic radius. So it's half the distance between the nuclei of 2 identical covalently bonded atoms. So these are 2 identically covalently bonded atoms, and we're taking half the distance between their nuclei to give us. Now, if that's not clear to you why that's the atomic radius, well, if we were to take half this distance, split it in half here, it would be there. And if we go up, it's obviously from there to there is the same as the radius of a circle. So that's why we take this distance and divide it in half. So that gives us the atomic radius. So what is the atomic radius again? Just to clarify, it's half the distance, or the distance divided by 2, which is half the distance between the nuclei of 2 identical, and they have to be the same atom, otherwise the 2 atoms will be different sizes, of 2 identical covalently bonded atoms. This here is what we call the atomic radius. It's a good idea to make a note of this definition. So this is a definition, and we know our definitions, we've got to learn them word for word. Okay, so what I'd like you to do is I would like you to pause the video, and I would like you to take that down now, please. Okay, so you should only be watching the video if you have paused the video and taken that down for me. Okay, so that is the atomic radius. Now, of course, what we're going to be doing in this chapter is we're going to be looking for patterns. We're going to be looking to see what happens when we look around the periodic table at, for example, atomic radius. What happens as we move down the table or across the table? What happens to the radiuses of the different atoms? Well, the first thing to say is that the radius of each atom is different. So each atom is a different size. They have a different radius from the nucleus to the outer edge, will be different in size. The main reason this distance can increase is when we compare atoms with different numbers of energy levels. Okay, so if we take, for example, 2 lithium atoms like this. So if this is a lithium atom, and this is a second lithium atom. So this is lithium atom, and this is a second lithium atom. So these are 2 atoms, covalently bonded, and they're identical. Okay, well, these have electrons. Lithium atoms have 3 electrons. They have 2 in the first shell, and they have 1 in this outer shell. This one is the same, and it's got 2 electrons in the first shell, and it's got 1 in the second. And the key thing here is, remember, if we want to know if we wanted to know the atomic radius here, we would go from the nucleus of each one. We would measure the distance between the 2 nuclei. So from here to here would be the atomic radius. Oops, sorry. From here to here would be the atomic radius of lithium. Now, of course, there are 2 energy levels here. This one here is n equals to 1, and this one here is n equals to 2. Lithium only has electrons in n equal to 1 and n equal to 2 because it's only got 3 electrons. Now, if we go in the periodic table in the same group as lithium, which is group 1, go to the next one down. The next one down is sodium. So sodium also has 1 electron in the outer shell. So I'm going to draw 2 sodium atoms now. So this is a sodium atom. It's got 2 electrons in the first shell. It's got 8 electrons in the second shell. 4, 5, 6, 7, 8. It's got 8 electrons in the second shell. And it's got 1 in the outer shell as well, but this is in the third shell. Okay, it's got 1 electron in the outer shell, but it's in the third shell. As you can see here, the atom is obviously bigger. And this is because it's got an extra shell. It's got more electrons, which means it's got an extra energy level. So instead of drawing, I'm just actually going to copy it. It just makes it easier than drawing it out again. And it's the exact same atom, as you can see. And to get the atomic radius here, again, I would do the same thing. I would measure the distance between the nuclei and divide it by 2. I would do it like this. And like this. And I would measure the distance between them, which is obviously a bigger distance than for lithium. And I would divide that distance by 2. And I would have to divide this one by 2. So get the distance between the nuclei and divide by 2. So that's the first thing that causes a change to the atomic radius. If you add more energy levels, then you increase the atomic radius. So as you move down a group in the periodic table, you add more energy levels and the atoms get bigger. So that's the first thing that's going to cause the atomic radius to change, is the number of energy. Now, as we previously discussed, the nucleus is home to the positively charged protons. So we're just going to take a look at these now. Okay. So here I am drawing the nucleus. For example, we have a nucleus that's got, make that pen a bit bigger. Say we have a nucleus that's got 1, 2, 3 protons. So in the nucleus, we find the protons. We find a second type of subatomic particle, which I'm going to draw in green here, and these are called neutrons. So what's important here, what I want you to focus on though, is the red ones. So the red ones are protons. Now, this is the nucleus, and the nucleus is a nucleus with 3 protons. This is a nucleus with 3 protons, as you can see by the 3 red circles. Now, neutrons do not have a charge, so neutrons are neutrally charged. They have 0 charge, and the protons have a +1 charge each. So this is a nucleus with 3 protons, which means that the overall charge is +3 charge. So this nucleus has a +3 charge. Say we compare that to another nucleus. Say we compare it to this nucleus, which has this is a nucleus with 7 electrons. Or 7 protons, not electrons, apologies. And it happens to have 7 neutrons as well, which are shown in green. Here. 1, 2, there's 7. So 7 protons and 7 neutrons. That's a nucleus with 7 protons. This is a bigger nucleus with more protons. So this is a nucleus with a +7 charge. So we call this charge the nuclear charge, because it comes from the nucleus. the nuclear charge. So the nucleus on the right has a higher nuclear charge than the nucleus on the left. It has a +7 charge, whereas the nucleus on the left only has a +3 charge. So we say that the nuclear charge has increased. Now, so the overall positive charge on the nucleus is referred to as the nuclear charge. Now, what has this got to do with electrons? Well, the nucleus is positive. It's always positive. It's got a positive charge. So I'm drawing it as a nucleus that is positively charged. Remember that the atomic radius is controlled by where the electrons are in the outer shell. So I'm going to draw electrons. There are 2 electrons, we'll say in the first shell, say this is lithium. There are 2 electrons in the first shell, and there is 1 more electron for lithium, and it is in the second shell here. Now, why can't this electron head off and go wherever it wants? Why does it stay in this general region in the second energy level? Well, electrons in the outer shell are kept attached to their atom due to the attraction they have for the nucleus. So because electrons are whizzing around, remember electrons are negatively charged, they have an attraction to the positive nucleus. So they have an attraction to the positive nucleus. We say they have an attraction to the nuclear charge. They have an attraction to the nuclear charge. That is what keeps electrons from heading off and going wherever they want. Now, this is an atom which just has electrons in the first and the second energy level. So it's a small atom, it's only got 3 electrons. It's got 2 electrons in the first shell, and it's got 1 electron in the second shell. However, when we look at a bigger atom, and we have, for example, I'm just actually going to draw it out. So we have a bigger atom. So here's the outer shell. So we have the nucleus, which is positive in the middle. We have an electron in the outer shell. So this here was lithium, 3 electrons, and say here this one is sodium, which is just below lithium in the periodic table. So we have lithium and we have sodium. Now this one, they both have 1 electron in the outer shell, but this one has a second shell inside like this that is full of electrons. It's got 8 electrons. So sodium has 2 in the first shell. It's got 8 in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And it's got 1 in the third shell. As you can see, there's an extra shell, what we call an inner shell, full of electrons. So the inner shells are full of electrons. Lithium does not have this. So when you have the outer electron in a higher energy level, there are more electrons in inner shells. And these electrons basically repel the outer electron. So just like before, the electron in the outer shell is still attracted to the nucleus. So it's still an attraction to the nuclear charge, but they are also repelled by electrons in the inner shells. So I'm going to draw this in green. So they also repel the electrons in the inner shell, like this. So they repel, which means that they push each other away. They repel. So it's repelled by that one, and it's repelled by that one. So although it's still attracted to the nucleus, it is repelled by the shells in the inner shell. So this cancels out the effect of the nuclear charge, and this is called the screening or the shielding effect. Okay, so this here is called the screening effect. Screening effect. We say the inner electrons, the electrons in the inner shells screen the outer electrons from the nuclear charge. Another way of saying this is that what we call the effective nuclear charge, how effective it is, the effective nuclear charge sorry, this should be SC. The effective nuclear charge is reduced. And the reason why the effective nuclear charge is reduced is because of the screening effect of the electrons in the inner shells. This one has a higher effective nuclear charge because it has less screening. So a higher effective nuclear charge because it has less screening. Okay, so now we have two factors which affect the, the atomic radius as we move down the periodic table. So as we move down the periodic table in a group, so take a group like group 1 that we've talked about, lithium, sodium, potassium, and so on. And this is the same for any group. Choose any group and move down it, you'll see the same pattern or the same trend. When we're looking at patterns, we call these trends. So a pattern in the periodic table is known as a trend. So you might be asked about what is the trend in the atomic radius as you move down a group. Well, the trend is that the radius gets bigger, the atoms get bigger. Now, explaining why that is, well, there's two reasons that we've learned here. We've learned that basically you're adding more shells or more energy levels. So as you move down a group, you add extra energy levels. So the first one will be n equal to 1, the second one has an n equal to 2, the third one has an n equal to 3 shell, and so on. So that's one reason. As you add more shells or more energy levels, the atom is going to get bigger. The second reason is the screening effect. The screening effect is where electrons in the inner shells block or reduce the effective nuclear charge. So they block the pull of the nucleus on the outer shell electrons by repelling the outer shell electrons. Okay, so these are the factors that affect the atomic radius as we move down a group in the periodic. Okay, so just a quick reminder, these factors together, as we move down a group, we add extra energy levels and we increase the screening effect. And as we move down the table, the atomic radius increases, it gets bigger. Now we call these types of patterns on the periodic table trends. So the trend for atomic radius is as we move down the table, the radius gets bigger. And the reasons for this are shown in part 1 and 2. We've discussed them already, but it might be a good idea to just pause your video now and take that down for me, please. So pause the video and make a note of the reasons, nice summarized reasons why atomic radius decreases going down the table. Okay, another trend in atomic radius is when we look at what happens when we go across the table. So from left to right across a period. Now, as we saw up in question 9 up here, if we just go back up to question 9 where we answered before, question 9 is shown here. When you move from left to right across a period, what happens to the number of protons? That was the question. In terms of the number of protons, what happens as you move from left to right across the period of the table? So when you move from left to right across the period of the table, the number of protons increases. So we've already learned that. Now, as we see here, what happens when we move across the periodic table to the atomic radius then? Well, as you move from left to right across the period of the periodic table, what's happening is you are adding protons. And remember, when we add protons, just like up here, this was 3 protons going to 7 protons. Well, as we move to left to right, we add more protons, we increase the nuclear charge. So increase the nuclear charge. So that's what happens as we move from left to right across the table. We increase the nuclear charge. Now, what effect does this have? Well, if we increase the nuclear charge, we obviously attract the electrons towards it more. So we attract the electrons in the outer shell. This gets stronger then. So when we have an increase in nuclear charge, the force of attraction that the electrons have gets stronger, and that's obviously going to draw them closer. So that's going to have the effect of making the atomic radius smaller, because the atoms are going to get smaller as the electrons get attracted towards the positive nucleus. And this all happens as we move from left to right across the table. We don't add any extra energy levels. So there are no extra energy levels. So the electrons aren't getting further away into further away energy levels. So we say that the effective nuclear charge is increasing. So increasing effective nuclear charge. It's getting bigger because the electrons aren't getting further away into further energy levels, and the nuclear charge is getting higher. So in summary, the value of atomic radius decreases, gets smaller. So decreases means gets smaller. So the value of atomic radius decreases going across a period of the periodic table, because the effective nuclear charge of the nucleus increases going across a period. So we've got more positive charge as we have more protons in the nucleus. This pulls the outer electrons closer to the nucleus, so the atom gets smaller. So as the nuclear charge gets bigger, the atom gets smaller. There is also no increase in the screening effect, as all elements in the table are all elements in the same period have the same outer energy level. Yeah. So as you move across and you go through the elements of a period, they all have electrons in the same outer energy level. You're not adding any extra energy levels. So they are the reason why the atomic radius gets smaller. So just in summary, I have a nice diagram here, which kind of will help you to figure that out. See, as we go down a period, the radius increases. So you need to know what happens. It increases, and you need to be able to explain why. As you move from left to right, the radius decreases, as you can see, starting big, smaller, 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 and so on. Okay, and the reason for that, again, is that we have an increasing effective nuclear charge. The nucleus is gaining more protons every time you go over by one, and we're not adding extra energy levels. There are no new energy levels. So that means that electrons are getting sucked closer and closer to the nucleus. Right, it's time to do some practice questions now on that. Sorry, actually, do you know, I'm just going to leave that screen up there for you to take a note of that stuff there. So pause that, take a note of the trend, what happens as you go across, and the reasons. Okay, time to do some practice. So what I'd like you to do is I want you to do these questions, and I want you to please do them from memory. So put away the notes that you've taken down, and I want you to do these from memory, please. Pause the video and do them now. Okay, so as you can see, you should only play in the video now if you have tried them questions. As you can see, there is some retrieval stuff in here again, always retrieving information from previous topics. So state the noble gas configuration of silicone using noble gas configuration. So silicone, go to your periodic table. Silicone has 14 electrons, and we're going to use a noble gas abbreviation. So Si. The electronic configuration, we're going to use noble gas that comes before silicone, which is neon. So the electronic configuration is the same up to neon. And then we're in 3s2, 2p4, 2p2, sorry, 2p2. 3s2, oh, this is 3p2, apologies. 3s2, 3p2. So you've got neon, square brackets neon, it's the same as neon up to there, and then you've got 3s2 and 3p2. Right, there's the answers to the rest. So I want you to pause your video, pause the video and make corrections to your answers now. Okay, that's it for atomic radius and the trends in atomic radius moving down the table and across the table. I'm going to see you in the next video, and we'll talk about a trend of a different trend that we can spot on the periodic table.